Right, so last up we have transformers. So we've made our electricity, or generated our EMF in a coil of wire. We've analysed that, and now we want to get it to our consumers. And in order to get it to the consumers, we have to consider what voltages we want. Actually, when electricity is produced, when EMF is produced in power stations, it tends to be reasonably high anyway. So you would need to change that down, because a large potential difference means sparking, which means risk of kind of electrical fire. So we change the potential difference, and we use a transformer to do it. This is a GCSE topic. You probably remember it from GCSE physics. So you put an alternating current in. You have a potential difference across your primary coil. This is the primary coil. This is the secondary coil. So you have the primary coil. You have the primary potential difference, and the primary coil is looped around a certain number of times. Then the secondary coil is looped around a different amount of times, and the ratio of the loops gives you the ratio of the increase or decrease in potential difference, whether it's a step up transformer or a step down transformer. The alternating AC current around here creates an alternating magnetic field in the core. The alternating magnetic field travels the whole way through the core. The wires are not in any way, shape. The wires need to be insulated. No current flows through the coil, or no current should flow through the coil. But then the alternating magnetic field set up inside the coil, so alternating north, south, as this potential difference goes positive, negative, induces an alternating potential difference across this coil here, and obviously a current will flow. More coils here mean you're going to have a step-up transformer, because you're going to have a bigger potential difference out. Again, this is a GCSE topic, and I'd recommend at this stage going maybe back through GCSE notes or find a GCSE video on it, just to make sure you completely understand it, because this is just like adding a bit to it rather than going through it from scratch. Now, but I can make a video going through it from scratch if you think it's necessary. I know you guys did different things on your GCSEs. So we then have this sort of national grid situation. At a national grid, we have the electricity produced in a power station. We then have step-up transformers to really increase the potential difference to transport the energy along large distances without having power losses. It's nothing to do with the speed of transporting electricity. There's no problem, right? Speed is not a problem. It's about power losses. So if we have a really high potential difference, we can reduce the current and have the same amount of power through P is IV. If we have a really high potential difference, P is IV, and a low current, we're going to have the same power produced or the same power transferred. Now, but the current is the thing that causes power losses, because power is I squared R, and because the current is squared in that bit, we have a really high current. We're going to have a lot of energy loss due to heating of the wires. So we make the current really low, so there's less power loss, so it's more efficient. And again, it's about efficiency, not about speed. It's more efficient because there's power loss, but then we step it back down to, VRMS 230 before we put it into people's homes, just to avoid the large potential difference creating kind of sparks and things. Now, one of the problems in transformers is production of these things called eddy currents. So eddy currents are the free electrons inside the iron. This is an iron core. Feel the effect of the magnetic field. They start to move, and when they start to move, they can sometimes set up these tiny little sort of currents. They look like little eddies in a river. That's why they're called eddy currents. Set up little tiny currents. And the problem with that is twofold. First of all, the currents themselves will generate heat and lose power for your process, so it'll be less efficient. But the other problem is that Lenz's law states that the current produced from this magnetic field will oppose the magnetic field changing it. And so it kind of has a double effect. Not only does it do heating, but it also reduces the impact of the magnetic field. Because if that magnetic field is north, trying to make this induce, the eddy currents will produce the south, right? So they'll try and oppose the or produce the north, trying to oppose the change. The solution to this is lamination. So laminate paper, lamination, like croissants are all about lamination. Lamination is when you have a layer upon layer. So what they do is they have the iron, but they have a layer of iron, layer of plastic, layer of iron, layer of plastic, really thin, and build it up. And that doesn't affect the the quality of the magnetic field produced, but it does mean these eddy currents can't flow as much. It's almost impossible to get rid of them. And so you have an efficiency equation for a transformer, right? So the efficiency is the current of the secondary times the potential difference of the secondary divided by the current of the primary times the potential difference of the primary, or basically the power out divided by the power in, which is efficiency anyway, because P, power, is IV. So like I say, that's it for transformers. Straightforward, and the end of this bit of magnetic fields, which I think is one of the trickiest ones. So well done for making it through.